William D. Middleton was a licensed professional civil engineer and a respected writer of transportation technology with several traction books published. These books include The Interurban Era, 1961, North Shore, America's Fastest Interurban, 1964, and When Steam Railroads Electrified, 1974. In 1950, Middleton earned his undergraduate degree in civil engineering from Rensselaer Polytechnical Institute. From 1950 to 1979, he was an engineer with the United States Navy and retired as a commander. After retiring from the Navy, he served in the position of Chief Facilities Officer at the University of Virginia. From the 1950s until 2011, he was an active railroad historian and a writer who published over 20 books with numerous magazine articles. Unlike Jones, Middleton wasn't a trained professional historian. Although Middleton's book, Frank Julian Sprague, did a good job of laying out Sprague's career, the part that deals with Sprague's motor problem on the trolley line in Richmond, Virginia, has some inaccuracies. Middleton is not alone in this respect. Others have made the same error. Before we look at where Middleton went off the rails, we'll look at what Sprague did in Richmond. Sprague believed that a constant-speed motor would be best for trolley service. He had been writing about such a motor from his earliest work. His patents of the late 1800s show this as well. U.S. Patent 315179, 7th of April 1885 says, with any given potential at the armature terminals, a constant speed may be maintained under varying loads by varying the strength of the field inversely with the variations in the load, so that when the load diminishes, the counter-electromotive force is increased, whereby the speed remains the same, and vice versa. In his 1934 AIEE article, Sprague, Digging in the Minds of the Motors, Transactions of the American Institute of Electrical Engineers, May 1934, page 697, he says, our initial industrial motor development was based on the important fact that on a constant potential circuit, the mechanical effects, variations of speed and power out, of a motor could be controlled by inverse variation of the strength of the magnetic field to determine the differential of the line and motor electromotive forces. Also, with two magnetizing fields, one of high resistance across the line for the main field excitation, and another of a few turns in opposition to it and in series with the armature, it would be possible for certain proportions to operate a motor at the same speed under varying loads. This is a schematic representation of a direct current shunt motor. It was the most common motor at that time. The shunt motor has its field, F sub P, in parallel or shunt with both the armature, A, and the supply voltage, V sub S. The shunt motor does not have a constant speed characteristic. Its speed decreases with increasing load torque. This is referred to as a drooping load characteristic. Drooping means that as the torque required by the motor's load increases, the speed drops. This is the mechanism by which the motor takes on load. A decrease in speed would allow more current to be drawn by a motor to produce an increase in torque. This increase in torque is required when climbing a hill. The operator typically used some sort of drum controller to reduce the resistance connected in the motor circuit, which applied additional voltage to the armature. This in turn supplied that additional torque needed to bring the car back to the required speed. The opposite was true when going downhill. This is known as armature voltage control and was the accepted method of speed control at the time. But Sprague wanted to automatically control torque to control changes in speed. Sprague was aware that James Watt had solved this speed problem by inventing a flyball governor. When a reciprocating steam engine was driving some load, such as a water pump, it would slow down if more water was required and speed up when the water requirement lessened. The governor increased or decreased the input of steam to the engine to hold the speed constant. In Sprague's U.S. patent number 295454, we see a controller that did the same thing, but with an electric motor. This patent is dated the 18th of March, 1884. We can see here a flyball set up on the top right side of the DC motor. The governor connects or disconnects portions of the motor's field in order to maintain speed constant. On page 40 of Frank Julian Sprague, Middleton says, Sprague's motors were well designed and incorporated several new features, and their merits were quickly recognized. The motor operated at constant speed, regardless of changes in the load. The figure shows the curves of a differential compound motor and a shunt motor. The differential motor has its no-load and full-load speed virtually the same. It is more or less a motor that operates at nearly constant speed. Like the shunt motor, the differential compound motor also has a shunt field, F sub P. But in addition to a shunt field, there is also a series field, F sub S. This series field operates in such a way as to weaken the overall field. For a detailed description of how this happens, refer to the IEEE article, A Lurid Green Glare, mentioned in the notes at the end of this video. The problem with the differential motor is that, in order to keep the speed from dropping, it draws even more current than taken by an ordinary shunt motor. The hills in Richmond were the cause of this increased current that resulted in Sprague's brush problems. It was just a simple matter that, in effort to maintain a constant speed, the differential compound motor drew too much current. What was actually required was a series-connected motor. Benjamin Lammy, a Westinghouse employee, was responsible for the development of the series motor in traction service, but this was still a decade or two down the road. The series motor was, in many cases, still is, the traction motor of choice. Sprague himself was aware that things were far from perfect at Richmond. In his article in the Engineering magazine, April to September 1894, he wrote, "It was a daily occurrence to see a loaded car climb a grade with a lurid green glare lighting up the track. At about this time, $9 worth of brass per day, milled off the rough bars of the commutator, lined the track with a glittering path. Not a single trip was made without inspection, with generally a change of brushes or some other repair. But that was not all. Every armature was unwound, the body shortened, and then rewound. Disabled armatures were numberless, and to keep the road in operation, tons of machinery was shipped by express." Continuing, he says that gradually we saw our difficulties lessening, and little by little the number of cars in operation was increased. This gives the reader the impression that the problem was finally solved. Other biographers of Sprague have noted this motor problem, some haven't. Even so, most writers give the impression that Sprague eventually sorted out his motor problems. But an account by one of the Richmond superintendents, S. W. Huff, writing in the Cornell University Sibley Journal of Engineering in October 1912, tells a different story. On page 2, Huff says that in 1890, the operators of the Pioneer Electric Railroad in Richmond, Virginia, had announced that after a thorough test, they were forced to admit that electricity as a means of propelling cars was a failure. On page 4, we read that there were times when only 1 or 2 cars were in operation and that fuel coils required constant rewinding. The motor problem often gets lost in the list of Sprague's important accomplishments. Nonetheless, Sprague's motors, the heart of his trolley system, were not a success.